Hello, everybody. This is the recorded version of Chapter 2, Part 1. We're doing this because we missed a class because of the ice day. And so the second part of this chapter will come to you in person, hopefully on Monday. But until then, follow this lecture along the lecture slides. And we'll be building on this quite a bit on Monday in our second lecture of Chapter 2. So I'm going to go to a screen share and take you through this first portion of the chemical basis of life chapter. All right, so let's make this full screen if we can. Here we go. So the reason why we have a chapter about chemicals in this anatomy and physiology class, because we observed way back in chapter 1 that one of the basic life processes is metabolism. Metabolism is this series of chemical reactions, hundreds of thousands of them happening in our body, and those chemical reactions must go on in order to maintain life. We'll be seeing several examples of that. We'll stay as close as possible to examples for normal anatomy and physiology. Just to start with this, the textbook has somewhat good information about the structure of atoms, nature of chemical bonds, and so please review that from your textbook. For example, like the atoms are made up of a nucleus, which has protons and neutrons, and then around all that has electron shell. Please take a look at that. It is sufficient what our textbooks say with this regard. So what we're going to explore here in this chapter, after some generic observations, I'm mostly focusing on the inorganic chemicals that making up our body. So when you look at the periodic table of elements, you see individual elements that eventually form chemical reactions with each other. Here are two of the elements that are making up most of our body, hydrogen and oxygen. And under the right circumstances, these reactants, the starting materials, can form products, the end result of the chemical reaction. There are two other elements that are represented in a major fashion in our body, nitrogen and carbon. What's perhaps most noticeable in these chemical reactions are these stick figures that you see here between individual atoms. Those are chemical bonds. The chemical bonds are important to hold atoms together. They represent bridges that also represents energy. So this is a really important recognition that chemical bonds represent energy. When chemical bonds form, like in this chemical reaction, they hold onto an amount of energy. And when chemical bonds are broken, they release the energy contained in that chemical bond. And so let's take a look at how chemical reactions can be classified based on this storing energy in bonds or releasing them from bonds. I'm going to go right here. So take a look at these two types of chemical reactions. Here is where the top graph here represents a chemical reaction where there is energy released. This is typical where in a chemical reaction, chemical bonds are broken, and that surplus energy is released into the environment. These chemical reactions are called exergonic reactions. In a part two of this chapter 2 lecture, we'll see very good biological examples of that and the absolute necessity to follow this. So there's a group of reactions in the body that release energy. And then take a look at this bottom. There are chemical reactions in the body where energy is absorbed. This is a group of chemicals, group of chemical reactions where new chemical bonds are formed and energy is needed to be incorporated into those new chemical bonds. So these two types of chemical reactions divide the chemical reactions into two groups. We'll be later on calling the top exergonic reactions where energy is released, catabolic reactions in general, and these type of reactions that go on in the body, we'll be calling them anabolic. So examples here for the top, the chemical use of blood glucose, blood sugar in the body releases energy. If you want to make this molecule called ATP, we are looking at an endergonic reaction. And again, in part two lecture of this chapter, we'll be seeing this a little more detail, how this is happening. For chemical reactions to occur, we need to overcome a barrier. So take a look at this activation energy barrier. The reason why this barrier exists between two reactants at the beginning of chemical reaction, because all chemicals on their outer surface are made up of negatively charged electrons. Negatively charged objects prevent their union, they repel each other. And so we have to smash these molecules together. We have to overcome this activation energy barrier, this repelling force. And that happens usually at high temperature in a chemical lab. How chemical reactions occur in our body when the temperature is relatively low. This activation energy needs to be overcome for chemical reactions in the body, and this will take us to another physiologically really important part. So instead of changing concentration or temperature in our body, to speed up chemical reaction in our body, we use catalysts. Catalysts are chemicals that do not participate in a chemical reaction, they just assist. These assisting chemicals, catalysts, are absolutely necessary for metabolism to happen in our body. Without these catalysts, there's not much going on in the body, chemically speaking. So where do we get these catalysts? A very basic observation is that in our bodies, to maintain homeostasis, to carry out metabolism, we use enzymes. Enzymes are proteins by their chemical nature. They are catalysts. And without enzymes, our bodies would not work. We could not maintain homeostasis because chemical reactions would be either slow or not going on whatsoever. So these protein catalysts, the enzymes, are tremendously important to maintain homeostasis. We are looking at an example here to illustrate what happens when an enzyme is not doing its job. So our example here is in the digestive system. When we consume dairy products, we consume this sugar, lactose. Lactose has two halves to it, a glucose and a galactose half. If you want to absorb this lactose in a small intestine and move it into a bloodstream, lactose need to be split into its component, glucose and galactose. This splitting activity is coming from the enzyme lactase. So this is a catalyst. And so when the lactase enzyme is working, we have no problem eating dairy because the milk sugars component, glucose and galactose, will be absorbed after splitting the lactose. Now, what happens in individuals who are lactose intolerant? In lactose intolerant individuals, this lactase is either mutated or altogether missing. And so in lactose intolerant individuals, the lactose sugar is not split into two. Without lactase enzyme, the lactose molecule moves onto the large intestine and bacteria will digest it, and that can cause diarrhea, cramping, bloating, gas production. So missing the lactase enzyme is not a lethal defect in our body, but it definitely makes one's life difficult. If you know anybody who has serious lactose intolerance, they avoid products, food components with lactose in it because they know that the outcome is not very pleasant. There are other enzymes in the body whose absence or mutation will be lethal. As we go on in this class, we'll be mentioning a number of conditions where proteins, sometimes enzymes will undergo mutation, and that functional defect will have severe consequences on the body, inability to maintain homeostasis. So this was here a relatively mild illustration of why enzymes are important for chemical reaction in the body. You would think that lactose would just split by itself in the small intestine, but not so. At our core body temperature, lactose does not split. It needs a catalyst, an enzyme, excuse me, namely lactase. So this is the importance of that activation energy, overcoming it by catalysts. And now we are seeing that in biological system in our body, the catalysts are called enzymes. So here is the two groups of reactions in our body. Anabolic reactions, when two or more atoms or molecules combine together, we are forming new chemical bonds. And so these reactions are typically endergonic because they absorb energy, the energy that goes into the chemical bonds. Typical biological example, taking amino acids and form a long protein. We'll be seeing in chapter 3 that on ribosomes, this process goes at a breakneck pace in all of our cells. So we have many, many anabolic reactions in our body. This is a natural set of chemical reactions in our body. We need energy for this. Thank goodness we have catabolic reactions in our body because these reactions split or break chemical bonds. They tend to be exergonic, release energy. So energy liberated here in catabolic reactions can be channeled to the location of the anabolic reactions. And in all of our cells, there's the streaming of energy from the location of catabolic reaction to the location of anabolic reaction. This is just hopefully illustrating well that chemical reactions are necessary. And inside our cells, the chemical reactions are organized into compartments and groups. and energy-releasing exergonic catabolic reactions are there to supply energy for the anabolic reaction. We'll see a very essential component for this energy transfer in the second lecture here in chapter 2. So our view of the chemicals that are necessary to life, we'll be focusing on first inorganic compounds, and in the second lecture, the organic compounds. So what the heck is an inorganic compound, an inorganic chemical? These are simple molecules, maybe 3, 4, 5 atoms joined together. We'll be seeing a very popular example of water. Water has 2 hydrogen atoms and 1 oxygen. So to make water, all you need is 3 atoms. Excuse me. Most inorganic chemicals have no carbon in it. There are exceptions. The carbon dioxide that we exhale is considered inorganic despite the fact that it has carbon. Organic molecules, as you'll see in the second lecture, not only has many carbon atoms are linked right next to each other, and much more elaborate, a lot more complex, and much larger molecules than inorganic ones. So our major example here with the inorganic chemicals will be water, H2O. So why do we have so much water in our body? About 55% of our body weight is made up by this chemical. What could it possibly do? So water, first of all, is the most important environment, hydrophilic environment for chemical reactions. So the water's role as a solvent means that chemicals dissolved in water find themselves at a very comfortable spot to carry out chemical reaction. In addition to surrounding and providing the best environment for chemical reactions, water sometimes participates in chemical reaction. So water will become a reactant or is a product. In hydrolysis reactions, and we'll see examples of this in the second lecture, hydrolysis reactions, water is needed as a reactant for hydrolysis reactions to occur. In dehydration synthesis reactions, water is a product. So this is the second important aspect of water participating in chemical reaction as a reactant or as a product. Here are 2 more physical properties of water that our body takes advantage of it. First, let's talk about the high heat capacity. Heat capacity means that water can absorb a large amount of heat energy without starting to boil. This is great because sometimes our body is exposed on the outer surface to a large amount of heat. Thinking about cutting the grass at 105-degree temperature in the middle of the summer, you're out in the blazing sun, your outer body surface can heat up significantly, but we don't see water starting to boil in our skin because water absorbs heat energy without coming to boil. So this is great energy, great property of the water. If you think about the water content in our blood, heat can be moved from one place in the body because one place in the body to another because water absorbs heat and can move it very easily. The second physical property of water is that heat of vaporization is high. Now, this is a totally different deal. If we want to evaporate water, turn it into steam, it takes a lot of heat. We take advantage of this when we regulate core body temperature. When we overheat, we have hyperthermia. Our sweat glands are turned on and sweat. which is mostly water, poured out onto our body surface. As the water evaporates, it takes with it a lot of heat energy. When evaporation takes heat energy away from our body itself will cool down, and therefore core body temperature can be returning to the normal. So this is where we take advantage of the high heat of vaporization during maintaining homeostasis. Excuse me. We'll see water as a lubricant in the lab. We will be talking about, by the time you listen to this, the lab will be over. So we have talked about fluids such as peritoneal fluid, pericardial fluid. We talk about pleural fluid. These fluids provide lubrication in part in between body parts. We also have fluid in synovial joints. We'll take a look at this in chapter 9. So this aspect of water as a lubricant comes up several times in this anatomy and physiology class. And then here is an aspect of water that was difficult to suspect at the beginning. Let's take a look at what's happening to molecules that are put into water. So when water surrounds molecules, if these molecules are ionic molecules, such as potassium chloride here in this beaker on the right, or potassium hydroxide or hydrochloric acid, these ionic molecules are teased apart in water. So the consequence of that is that, for example, sodium chloride or potassium chloride, they are found in their ionic form in bodily fluids. This will be super important because potassium ions, sodium ions are essential for the workings of our nervous system. We'll talk about that more in chapter 12. But then here is something totally unexpected. When an ionic compound contains a hydrogen ion, and this molecule is teased apart in water, hydrogen ion is liberated. And at first, there is nothing super suspicious about this. But then chemists in the 1800s noticed that when this type of reaction goes on in water, the presence of hydrogen ions can speed up or slow down chemical reactions. So chemists studied this a lot more, and they started to measure hydrogen ion concentration in the body. Being chemists, they had to give this a name, and they gave this hydrogen ion concentration the name pH. So pH is a negative logarithmic measure of hydrogen ion concentration. This is super important. It sounds pretty trivial, who cares type of topic, but this is a life-maintaining aspect of our body. Surprise. Why is that? Because chemical reactions in our body require a certain pH, a certain hydrogen ion concentration. Give too many hydrogen ions to a chemical reaction, it might slow down into an unexpected level, or it may speed up to an unexpected level. Take away too many hydrogen ions from a chemical reaction, and yet again, chemical reactions might slow down to an unexpected degree, or speed up to an unexpected degree. In plain English, we have to maintain hydrogen ion concentration at a homeostatic level. Therefore, there is such a homeostatic measure as pH of the body. Maybe a few more words of the body. So the scale runs from 0 to 14. At pH 0, there are huge amounts of hydrogen ions in a solution. At pH 14, the hydrogen ion concentration is almost nothing. The middle point between them, pH 7, is the neutral pH, where the hydrogen ions make up roughly half of the hydrogen ion and hydroxyl ion altogether. So the higher the hydrogen ion concentration, the lower the pH. So let's take a look at how is this shaping up in our body. But first, maybe let's take a look at the pH of blood. Here is our homeostatic range. In chapter 27 in AMP2, we're going to spend hours to explain how can our body maintain this pH. This is a very narrow pH range, so we cannot have too many hydrogen ions or too few. We'll be talking about this in AMP2, that if the blood pH falls below 7.35, we have a disorder we call acidosis. And if the pH goes above 7.45, the disorder is called alkalosis. None of them are good, and severe acidosis, alkalosis can kill us. Most patients who are waiting for a kidney transplant and they don't get it, they eventually succumb to chronic acidosis. So this is a life-threatening condition to deviate from these blood pHs. How do we maintain this in our body? We have several ways here, because we're talking about only chemicals in the body. We'll mention buffers. Buffers can change the pH when it goes to extreme, so extremely high or extremely low pHs can be returned to a more normal value by buffers. So here is the role of carbonic acid bicarbonate buffer system. If we have an excess of hydrogen ions here in this reaction, let's say pH dropped to 7.2, bicarbonate ions will combine with the excess hydrogen ions, form carbonic acid, and eventually turn to carbon dioxide and water. So we neutralize, we take out this hydrogen ion, and so we lower the number of hydrogen ions, we lower the concentration of hydrogen ions. And so this is one example of how buffers can return pH to the normal homeostatic pH value. Outside of the blood, there are compartments in our body where the pH is drastically different from the blood pH. If we take a look at the stomach, 1.2 to 3, the average would be maybe 2 or 1.8. Hugely acidic. Hydrochloric acid is made in our stomach that depresses the pH. Saliva is only slightly acidic. On the other hand, bile and pancreatic juice, secretions of the liver, the bile, and secretions of the pancreas are more to the stronger alkaline levels. So in compartments, pHs can be very, very different. However, in our blood and in our tissue fluids in between the cells, we have to maintain this pH, and our body pays very, very close attention to this. We have monitoring systems. We have effectors that maintain this pH. Again, a lot more about this come our way in AMP2. And so this is the first part to chapter 2, a little generic introduction into the words of chemical bonds, how they carry energy, how the energy flow in our body is represented between anabolic and catabolic reactions. We mentioned enzymes as essential catalysts for chemical reactions to happen in our body. And Then we mentioned a few words about water, the most important inorganic chemical in our body. So I'm going to close this screen share here. And I'm going to load this recording into your class shell and send a note to you about this recording. I'll hope to see you guys on Monday.